and beyond. So the floor is yours, Nicolas.
Yeah, thank you very much. Thank you for the invitation, and thank you for attending this talk. This presentation will be divided into 3 parts, but before I'm going to more details, let me briefly introduce my co-authors. So Christophe Cavazo is a professor at Télécom Paris. He used to be a postdoc in my group. Pierre Scuter is currently a PhD student in my group. Nicolas Daubijon is professor in Toulouse, and Robert Strachko is professor in Hungary in University of Pest. So this talk will be divided into 3 parts. So the first part will be really a high-level introduction of what I'm interested in. So as you will see, mostly low-rank matrix approximations, and in particular, non-negative matrix factorization. The second part will go into a bit more technical details about how we can characterize the uniqueness of non-negative matrix factorizations, because this is important in quite a few applications. And finally, I will briefly go into the topic I've studied more recently, which is going beyond NMF, so using nonlinear models and also deep non-negative matrix factorization. And as you will see, there is some connection with deep neural networks there. Okay, let me try with a high-level motivation. So what is the main purpose of my work? Mostly is to uncover structure in datasets, like many of us. And a powerful tool to achieve this is a so-called linear dimensionality reduction. It's really a basic approach to do this. So you're given a set of data points, which throughout this talk I will denote xj. And the goal is to try to approximate these data points using a linear combination of basis vectors, which I will denote wk. So you have n data points, and you want to find r basis vectors, so that each data point is well approximated as a linear combination of these basis vectors. So on the right, you have a simple illustration of 3-dimensional data points approximated by a 2-dimensional subspace, so with r equals 2. And so this dimensionality reduction is equivalent to low-rank matrix factorization, where the columns of the input matrix contain the data points, and where the low-rank approximation is expressed as a product of 2 factors, w and h, where the columns of w contain the basis factors, and the columns of h contains the weight necessary to reconstruct each data point in the basis w. So for example, h1 contains the weight to reconstruct x1 in the basis w. Sorry. So of course, such models are relatively simple, but they have many favorable properties. So they are typically easily interpretable, and I will show you 2 nice examples just after. We have a very good understanding from a theoretical point of view and also from an algorithmic point of view. So there are many such models that for which we can compute the optimal W and H factorization, and they are not data intensive and they are typically computationally cheap. So they have these properties that maybe neural networks don't have, at least in the original form. So this is a wide class of models which are referred to as constrained low-rank matrix approximations or factorization. So depending on how you define your model, you will get different problems. So of course, the most famous one is PCA, where you will define the error. So how you measure the error between the data points and the low-rank approximation using the least squares error. So this is the standard Frobenius norm. So this is the way you will measure the error. So I'm just recalling it. So just to make sure we are on the same page. So you want to minimize the least square error. So if you solve this problem, essentially you recover a principal coordinate analysis, and so you can compute optimally W and H using, for example, the truncated singular value decomposition. Now, if you change the model, for example, if you use a model called robust PCA, well, you will change the objective function. So now you will not minimize the least square error anymore. For example, you may want to minimize the absolute value between X and its approximation. So this is also known as the component-wise L1 norm. So if you do this, what will happen typically is that the residual, so X minus its approximation, will be sparse. And so for example, an application where it has been used successfully is so-called a video background subtraction in a video sequence. So we have a video sequence. So here it's just a mole somewhere. And so if you apply this decomposition, WH will extract the background, so a low rank part of the data, and then the residual W minus X, sorry, minus WH will be the moving objects in this video sequence. Another famous example is, of course, logarithmic matrix completion, where you have missing entries in your input matrix. So the most famous example is the Netflix matrix. So in 2006, Netflix launched a competition called the Netflix Prize Competition, where they provided a user by movie matrix. So each row corresponds to a user, each column to a movie, and each entry is the evaluation of the user for the corresponding movie. But of course, most users have not watched most movies, and so there are many missing entries. And so what you will typically minimize in this particular case, you will not be able to minimize over all entries because you have not observed all entries. So you will have an objective function of this form, where you only minimize the error on the set of observed entries, which are denoted here omega. And so there's been extensive work on this particular model because it has, of course, implication in recommender systems, not only for movies, but also for books and so on. So all online commercial websites that are using such strategies to try to recommend users with items they will like so that they can make more money out of it, obviously. So this is a first thing when you design a low-rank matrix approximation model, how you compute the error, and this is, of course, crucial, but also what constraint you will impose on W and H. For example, the most naive model, which you know, and maybe you've not connected it to matrix factorization, is k-means. So for example, if I impose that in each column of H, there is a single non-zero entry equal to 1. So essentially, you do a one sparse constraint on the columns of H, you get k-means. In fact, for k-means, if you remember, you have the columns of W will be the cluster centroids, and each data point will be associated with a single cluster centroid. And so, for example, in this hyperspectral image, if we do a rank 4 factorization using these very strong constraints, you will get 4 clusters. For example, here, this is a Walmart. I will come back to this example later. This is the rooftop of a Walmart. You have the parking lot here in front. You have the roads. Then you have some rooftops of houses around. You have grass here and trees here. So these are rooftops here, trees, grass, and roads. And what I want to get into is yet another model. Of course, there is sparse PCA, which is closely related to dictionary learning, where you want W and or H to be sparse. But today I will focus on my favorite one, as you may know, which is non-negative matrix factorization, where you impose that the factors W and H are component-wise non-negative. So this is the standard model, standard optimization model that you would like to solve when you solve an MF. So here I'm using the least squares error, but as I mentioned, you may want to use different objectives depending on the application. And the particularity of NMF, non-negative matrix factorization, is that you want W and H to be component-wise non-negative. So as before, NMF is a linear dimension reduction technique. So we will interpret it in this way throughout the talk. So each column of X is a data point. It is non-negative. I will show 2 examples just after. You decompose it as each data point as a linear combination of these basis vectors, and they're also non-negative. So as we will see, this will allow us to interpret these basis vectors exactly in the same way we interpret the data. And the weights are non-negative, so you only have additive combinations. So you can only add parts, if you will, to reconstruct the whole. So geometrically, similar as before, except that now, because everything is non-negative, you have the data points are within the cone generated by the columns of W. So in this case, it's just a 2-dimensional cone, but in higher dimensions, it's a bit more complicated to represent. So now I will show you 2 applications of this model, trying to convince you it's useful to add these constraints, because as I will mention later, this problem becomes much harder to solve than without the constraints. So as you know, PCA can be solved efficiently. So unconstrained low-rank matrix factorizations can be computed efficiently. But when you add this constraint, you make the problem much harder to solve. Okay, let me begin this first application, which is called blind hyperspectral image unmixing. So we are given a hyperspectral image. So you have two spatial dimensions and 1 spectral dimension. So the particularity is that instead of having like 3 measurements like in a regular color image, in a hyperspectral image, you have much more measurements. So between typically 100 and 200 measurements for wavelengths. So typically either in ultraviolet or infrared measurements. So for example, for this particular image, so here you have the spectral signature of 1 pixel, which is a grass pixel, and the visible light is here. So we see there is a here because this corresponds to the wavelength of the green essentially. So this is the visible light wavelengths, and these are invisible to the human eye. And so it has applications to detect, for example, gases or to differentiate materials which have the same color in the visible range. So it has application for agriculture, military, and applications, and so on. So why does NMF make sense to analyze such data sets? So here we are given this image, and what we want to do is to automatically identify the materials present in this image, and also to know which pixel contains which material. And to do that, the most used model is the so-called linear mixing model. So here you have an example of the spectral signature of the grass. Here is the spectral signature of the road. And now, because these images are typically taken from airborne, the resolution is quite low. Also, these cameras, because they take a lot of, they have a high spectral resolution, they typically have a low spatial resolution. And so here you have, for example, in this pixel that contains 40% of road and 60% of grass, we will assume that the spectral signature of this pixel is 0.4 times the spectral signature of the road, because 40% of the light reflected by that pixel is reflected by the road, and 60% by the grass. And so the spectral signature will be 0.6 times the spectral signature of the grass, plus 0.4 times the spectral signature of the road. And this is exactly the NMF model. The weights are non-negative, and the basis vectors, they are also non-negative. So if you construct your matrix X such that each column is a vector, is a pixel, so it's the spectral signature of a pixel, you perform the NMF. Because W is non-negative, you can interpret these basis vectors as the spectral signature of the materials present in the image. And then the columns of H, it's called the abundance in this community. So each column of H will give you the abundance of each pixel of all the materials in each pixel. So let me show you the composition on this image I mentioned before. So this is a Walmart in Texas. So this is the rooftop, parking lot. There is grass, some dirt, trees, and so on. So if you perform a rank 6 factorization of this image, so this is a decomposition that you may get. So these are the 6 most important materials in this image: so road, grass, dirt, different types of rooftops, and the trees. So this you get as the columns of the matrix W. And then in the matrix H, you get the abundances for each material. So this first image is essentially the first row of H that has been vectorized, unvectorized. So it was vectorized to construct the input matrix X, because each row corresponds to a wavelength, to one image, each column to a pixel. So if you matricize the first row of H, you will get this abundance map of the first material, which is in this case the road. So you see it's very interpretable. It's very easy to understand what this decomposition did in this case. Of course, a posteriori, you need to interpret what it did. So you need to look at the image. Okay, this is the road, and so this is the spectral signature of the road, and so on for the other materials. So now let me show a second application, quite different in topic recovery and document classification. So in this particular application, each column of the input matrix X corresponds to a document, and each row corresponds to a word in the dictionary. So this is a so-called word count model. So each column here will contain the number of times each word appears in the corresponding document. So in this case, the first document, and so on for the other documents. So if you perform an NMF on these data sets, what do you need to extract? You need to extract a set of basis vectors, which are also non-negative. And also the non-negative linear combination need to reconstruct as best as possible all the documents. So this means that these basis vectors, they need to be used in quite a lot of documents. And because of this additive combination, this set of words, they need to appear simultaneously in many documents. So set of words that appear simultaneously in many documents are topics. So NMF will automatically extract topics from your input data matrix, which is non-negative. So it's a matrix of word counts. So let me show you this on an actual problem. So on the so-called TDT2 dataset. So this is a news outlet from 1998, which will be important when we analyze the topics from a different sources, so television, radio, and so on. So you can run this example with the code I have online, and I will show you how to do it. So you can load the data set. So here it's just to have the same dimension. So here we have about 20,000 words. So for example, the 1000th word in this data set is the word arms. And then you can check, for example, does this word appear in the first document? It's not, so it doesn't. So this word arms is not used by the first document. And for example, you can check it's used by one time, it appears one time in the 5th document. So these matrices are very sparse. So this is very different from the images where typically the input matrices are dense. So here we are in a quite different setting where the input matrix is sparse. And so now I can compute an NMF. So here I will use a rank 20 factorization. So this is probably, I mean, this is a question we get all the time in this business, let's say, is that we need to choose the rank. So it's a hyperparameter that you need to choose. And of course, it's not always easy to decide, I mean, what value is best for the corresponding application. But here I'm just arbitrarily choosing rank 20. So I'm going to compute 20 topics as the columns of W, and then the matrix H will allow me to classify the documents according to the topics they discuss. So I perform this factorization, and then I can interpret it. I will just select from each column of W the 10 most important words. So, so for this, I will so I will sort the entries in each column of W. So this is also easy to do because it's non-negative. So you can sort the importance of entries. If you perform the SVD on this matrix, it will be, you will get dense factors and that are difficult to interpret because the negative and positive weights, it's quite unclear how you interpret them. So now we can extract for each column the 10 most important word. I will put this in a topics matrix. So in this topic matrix, I will just put the words, the 10 most important words for each column of W. And then I can show you these topics. And so these are the topics. So the 10 most important words in each column of W. For example, the first topic is quite clearly the Lewinsky-Clinton scandal that happened in 98. In 98, there was also an Asian economic crisis. Another one that is nice is the Olympic Games that happened in Nagano in 98. Here you have a stock market topic. Here you have the Israeli-Palestinian conflict. Here you have the visit of the Pope to Cuba, went to Cuba. Another one is sports, I think, somewhere. Yeah, here you have American sport with Michael Jordan and also Super Bowl and so on. So this is what made, I think, NMF very popular, that it's very easy to use and very easy to interpret. So it has had quite success in this particular application. And of course, the models have been refined since then. You can use prior information and you can use a pre-processing of the data. Of course, as you may know, it's good to use some pre-processing of the entries, not use directly the word count. So you can use a logarithmic change that could be helpful. So there are many ways to improve the results, but it's just to show you how it can be used. So there are many other applications. I will not go into details. One famous one, at least this is one of the first one that was published, is about facial feature extraction. So in that particular application, each column of the matrix X is a vectorized facial image. The NMF is able to extract facial features, so parts that allows you to reconstruct all the faces. Okay, so I'm getting at the end of the introduction. I hope I convinced you this is a nice and useful model. And as I told you, this is a challenging problem. So so there are many things we can explore. So I mentioned the application, not all of them, but I'll give you some references later if you want to learn more. And there are quite a few important questions. So first one is of course, how we compute such decompositions. I will not go into this too much. How difficult is it to compute these decompositions? And then an important question is the uniqueness of these decompositions. So for example, in the hyperspectral mixing application, I want to guarantee to the user that I give him the spectral signature of the materials, not the spectral signature of something that allows you to reconstruct data points which do not correspond to true materials present in the image. So to do that, you need to obtain unique solutions. And this is what I will focus on in the first part of this talk. So here below, you have a very simple example of a non-negative matrix factorization, which is not unique. And so because it's not unique, it would give you different interpretations. In some applications, it's not too important to have uniqueness. For example, in facial feature extraction, you are not looking for particular features, and it does not really correspond to anything, to a physical model like in hyperspectral mixing. And in that application, you really want to recover the ground truth. A similar application where you have the same. Yes. Yeah, don't hesitate if you have a question to interrupt me. And so another application is also in chemistry. They also have these matrices of a spectra. So each column doesn't correspond to a point in space, but a point in time. You have a chemical reaction going on. You take measurements, spectral measurements every second, for example, and you also want to recover the spectral signature of the chemical compounds in the reaction and their proportion in the reaction over time. So in that particular application, identifiability, so uniqueness, is also very important. So this talk will be divided into two parts. I will, let's say, do 15 minutes, let's say, on the uniqueness. I will present quite simple results. So if you're going to go further, I will give you a reference, and then I will give you quickly some direction how we can go further this linear model. So please don't hesitate to interrupt me if you have any questions at this point. I'll be glad to answer them. So if not, let me start with this first part, uniqueness of NMF. So first, let me define what is a unique factorization. So for this particular section, I will focus on the exact decomposition. So of course, in practice, in the applications I mentioned, the decomposition are never exact because of noise, because of model misfit, and so on. But for the theoretical analysis, I will assume I have an exact non-negative matrix factorization, which here I denote W star H star. And so this factorization is unique or identifiable. So this word identifiable comes from the signal processing community. If and only if any other exact NMF of the matrix X is essentially the same up to permutation and scaling. So this is a standard definition, because of course in NMF, you always have this ambiguity. You can always permute two columns of W and 2 rows of H, we get the same factorization. And you can also scale. You can divide the first column of W by 10 and multiply the first row by H by 10, and you will get the same factorization. So you don't really care about these ambiguities. What you care about is up to scaling and this permutation to have a unique decomposition. I'm sorry, here there is a notation problem. So this should be WH here. So what are the results? Let me briefly summarize the most important results, I mean the most well-known results in this literature. So first, a quite simple and easy to check necessary condition is as follows. To have a unique NMF, you need that the support, so the set of non-zero entries in each column of W, not to be contained in the support of any other column. Because if it's the case, if the support of one column is contained in the support of another column, for example, let's say the support of the first column is contained in the support of the second column, then you can construct another factorization by constructing a new column W prime, which is the same column, the second column of W minus a little bit of the first column, because the support of this one contains the support of this one. This will remain a negative as soon as epsilon is small enough. So let me show this on an example. It's always easier on an example. So if I ask you, is this NMF unique? You can directly say, no, it's not unique, because the second column here contains the support of the first column. And how do you prove this? But you can just construct another factorization. So you remove from the second column the first column, and you construct this W2 prime here. And then the H, you need to update the H, of course, but this will be an additive combination, and so it will remain the H prime will remain non-negative. So you have two factorizations of the same matrix, but with different interpretation. So for example, if this would be a a word count matrix. So the first topic here will contain the first 3 words, and the other topics will contain all words, which is not very interesting. And in this second interpretation, the second topic will not contain the first and third words. So this is nice because this is very easy to check. So once you compute an NMF, you can check this support condition. If it's not satisfied, then you know your solution is not unique, and you may want to add prior information like sparsity priors or other types of priors to get a uniqueness. Now let me mention a sufficient condition, which is also relatively easy to explain. It's the following. So if the matrices W and H, they contain a non-singular diagonal matrix as a submatrix, then the factorization is unique. And the proof is also relatively simple, is because the identity matrix has a unique NMF. So you can, it's quite easy to convince yourself that you cannot decompose the identity matrix in another way than the identity times the identity. Of course, up to you can use diagonals also, but because the identity has its columns as the unit vectors, which are on the border of the non-negative orthant, and so you cannot reconstruct a column, a unit vector using something else than a unit vector because of the non-negativity constraints. So for example, if I give you this factorization and I ask you is it unique, and you can look for diagonal submatrices. In this case, of course, I constructed it in a way that it holds. So in this particular factorization is unique because W contains the identity matrix as a submatrix up to permutation and scaling, and similarly for H. So these are the two simplest and most well-known conditions. These are relatively old, let's say. And not more recently, I mean, not so recently, but 10 years ago, there was a much more interesting sufficient condition, which is called a sufficiently scattered condition. So let me focus on the matrix H. So the matrix H will satisfy the sufficiently scattered condition if the cone generated by the columns of H contains this green cone. So this green cone is tangent to every facet of the non-negative orthant. So it's quite spread in the non-negative orthant, although it does not contain the full non-negative orthant. So it's an intermediate condition, if you will. And it's called sufficiently scattered because to contain this cone, of course, you need to be sufficiently scattered within the non-negative orthant. So let me show you another representation where I normalize the columns of H. So now I just normalize everything so that everything is the unit simplex. So I'll project everything on the unit simplex. So here is a view from above. So this is the origin. So this is the unit simplex. This is the intersection of the unit simplex with this cone I mentioned. So the green cone before. And the blue points are just normalized columns of H. And so to satisfy the separability condition, so the first sufficient condition, you need that every column of H, you need that for every unit vector, there is one column of H which is multiple of that. So you will need, after normalization, that you will observe, in this case, 1, 0, 0, 0, 1, 0, and 0, 0, 1 as columns of H in this particular three-dimensional example. So this is quite strong assumption. And the sufficiently scattered condition is much weaker because you don't need to contain the unit vectors. You just need to that the convex hull of these normalized data points contain this ball here. In this case, it's just a circle. So you don't need to contain the unit vectors, but of course you need some sparsity because to contain the tangent point here, you will need at least 2 data points on this facet. And similarly for the other ones. So this requires some sparsity condition. And in fact, it's easy to show that this sufficient condition implies a necessary condition, obviously by definition. Okay, so most people, let's say prior to some recent work we've done, which I will present now. Finally, I present some of my own work. So they focus on this full identifiability. So I want W and H to be both of them unique. But there are many applications where it's not possible. For example, so here I have a data, it's synthetic data coming from the chemistry literature. So this each function here is corresponds to a column of W, and each here function corresponds to a row of H. So essentially, the matrix X will be the product of this matrix times this matrix, but it's just a visualization here. So the blue thing here, for example, is the first row of H, and the blue here is the first column of W. So if I show you this factorization, is it unique? You can check the necessary condition, and you will see that the support of the blue here, the first row of H, contains, for example, the support of the last row of H, the green one. So whenever the green one is positive, the blue one is positive. And so this factorization is not unique. So the question is it the end of the story? And the answer is no. I mean, we can still prove some interesting things, which we call partial identifiability. So although the full factorization is not unique, we studied the case. Okay, we cannot recover everything, but can we recover a subset of the columns of W and H? And this is what we define as partial identifiability. So the case column of W star is identifiable if and only if in any other and exact NMF of the same matrix, it has to appear up to scaling. It has to appear somewhere up to scaling. So again, there is a permutation and scaling ambiguity. And so we had this first relatively simple theorem, which I will maybe present on an example. So given that these two conditions, the orange one and the green one, are satisfied, then the corresponding column of W will be unique. So what are these two conditions? So let's start with the second one, which is easier to understand, is a selective window condition. So for the first column of W to be identifiable, I need that in the matrix H, there is the corresponding unit vector appearing. So in this case, 1, 0, 0. So this means that in the data set, I need this column to appear up to scaling. So it's quite a strong condition, but it's related to the separability condition, except that here I don't require separability for all columns, just one. So this is the first condition, the green one. And the second condition is a condition on the zeros, as expected, because we know we need some zeros, otherwise it's impossible to be identifiable because of the necessary condition I discussed before. So if you look at the set of zeros, you need at least R minus 1 zeros in the first column of W. And you need that the remaining entries of W here that corresponds to these zeros. So this R minus 1 times R minus 1 matrix. So in this example, this 2 by 2 matrix is full rank. So has a rank R minus 1. So if these two conditions are satisfied, which are very easy to check, then this column is unique. So in any NMF of this matrix, you will get this column up to scaling. So this is our first result. Let me apply now this on this simple rank 5 factorization. So can we, with this theorem, identify some columns of W or rows of H which are unique? So of course, everything I mentioned in this theorem here apply to H because of the symmetry of the problem. Everything that applies to a column of H applies to a row of anything that applies to a column of W applies to a row of H by symmetry of the problem, just by taking the transpose.
Nicolas, can I ask a question?
Yes.
Can you go back one slide? I think in the topic modeling, they have a similar condition about topics having unique words that are unique to that specific topic. I'm wondering if there is a connection between your work and that literature.
Yeah, exactly. So this was developed by the team by the team of Aurora in Princeton. They call this the anchor word assumption. Mm-hmm. And in fact, the separability assumption that I mentioned before here for W and H is called separability. In fact, this name separable was introduced by Aurora in 2013. So if the matrix H is separable, so this means essentially that in fact, so you have to look at the rows. So if the matrix W is separable, it means that for each topic, there is at least one word that is associated only with that topic. So that is only used by that topic. So if you look here, the first word is only used by the third topic. This word, the fourth word, is only used by the second topic, and the last word is only used by the first topic. So this is a so-called anchor word assumption or separability assumption in the NMF literature. So under that assumption, I will mention this a bit later, you can compute NMF efficiently, in fact. So here I discuss identifiability, but this condition has also implications on the algorithmic side. And so this is why it became very popular, because they had provable algorithm under this condition. And it's quite natural from a geometric point of view. So under this assumption, essentially, every data point will be a convex a conic combination of other data points, essentially. And so you can if there is no noise, you just need to identify the extreme rays of the cones generated by the columns of X. So it's a relatively simple problem. Of course, when there is noise, you need to work a bit more to provide error bounds. This is what Aurora and co-authors did, and I also have a paper on this topic. So this is a very good point. So this assumption that they are meaningful in applications. I mean, at least in some application. For example, in hyperspectral unmixing, this application requires that for each, so if you look at separability of H, for each, so recall each column here is a pixel, that for each material, each column here is a material, the spectral signature material. For each material, you need one pixel that contains only that material. This is the so-called, they call it the pure pixel assumption in hyperspectral unmixing. In fact, it's funny because this assumption was used for a long time in hyperspectral unmixing community, and like for more than 20 years, but only 10 years ago, it was kind of theoreticized a bit more rigorously, let's say. This was a long answer to a short question, but I hope it answers it. So let me now go back to this particular example. So can I now find profiles which are unique? So for that, I need to check these two conditions. For example, if I look at the blue factor, the first rank 1 factor, I see that the selective window assumption is satisfied because the blue one here is positive while all the other ones are 0. So the row of H here is positive while all the other ones are 0. So the selective assumption is satisfied for the blue profile. And now I need to check that when the blue profile is 0, the other ones have full rank. And okay, this is hard to see on a graph, but you can imagine that this part of the orange, yellow, purple, and green have full rank on this part. And so the green one, sorry, the green one is in fact the blue one here, this is identifiable. So in any factorization of the product of these two matrices, the blue one has to appear because of these two conditions. And you can do the same for other parts. So for example, for the yellow one, here you have the selective window, it's positive while all the other ones are 0. And when the yellow one here is 0, the other ones have full rank. And so again, we can guarantee that so this means that the yellow one here on the left is unique. And similarly, as I said, what we can do for W, we can do for H. So here, the green one is positive, while the rest are 0. So the selective window assumption is satisfied for the green row of the green function here. And when the green is 0, the other ones are positive. So at the end of the day, using this simple theorem, you can prove that in any factorization, you will recover these blue and yellow in the columns of W up to scaling a permutation, and you will get this row, this green row of H. So this is the first result in our paper, but we have more it's a technical result, which I will not present here because of time and just to remain clear. But if you want to know more, it's a recent paper that appeared in SciMax. So this finishes the first part. The second part, I will make it shorter, so I don't have so much time left. So I will really go high level here, but don't hesitate if you have questions after. I can go a bit further. So essentially, this NMF model is quite nice, but it is linear. So there are cases where it's not. I mean, it has limitations, and so one limitation is that it's a linear model, and so you cannot model nonlinear effects that often appear in application. And one example here, I'm just giving one example, is in the hyperspectral unmixing, you have often multiple reflections. So for example, in this example, the red light here is being measured after being reflected by the tree and then by the road. So this can be modeled as follows. So double reflections can be modeled. So the first part is the linear model. So for the things that only are reflected once before being measured. And then you can add this double reflection term where the basis vectors are the componentwise products of the spectral signature of the constitutive material. Because the light here will hit the tree, so the tree will absorb some of the light, and then the road similarly. And so the spectral signature of this red thing will be the componentwise product of the spectral signature of the tree times the time componentwise product with the spectral signature of the road. So this model was introduced in the hyperspectral unmixing literature. It's called the linear quadratic model. You have the linear part here and the quadratic part here. So of course, it's much more complicated. to estimate these parameters W and H, but it works better in application, in particular if you have three-dimensional scenes, like if you have trees or buildings, because you have these multiple reflections. So one way you can represent this model is again as a linear model where you have this P2W matrix here that contains the columns of W plus all the componentized products. So it's just another way to represent the same model in a more compact way. So you will put all these columns and all these columns together, and then all the weights together. So there was a quite nice result by Deville who showed that essentially this model is always identifiable as opposed to NMF. So NMF, you need quite strong condition to have uniqueness. But for bilinear NMF, so the bilinear case is that if you do not allow product of columns of W by themselves, so this is this condition here. So you assume that a tree, that the light will not reflect from a tree to the same tree essentially, or the grass twice on the grass, which is reasonable. So in this case, you need only full rank essentially assumption on W, on H, and on this P4. So P4 of W, what is P4 of W is all the componentized products up to order 4. So I will not go into the technical details why we need this, but it is quite nice. So under this full rank assumption, we have uniqueness without any other assumption. So it's stronger than for NMF. Of course, the model is more complicated. But although we have this nice result, the assumption is quite strong because this, for example, the requirement that the matrix H has full rank, it means that all the componentized products of two materials need to be observed. Because if let's say you never measure the grass, the tree that projects on the road and then back to the camera, then you will not be able to have this uniqueness condition. So you need that every pair of material at some point interacts, which is not very reasonable. And also you need this matrix to be full rank, this P4, which requires the number of spectral signatures to be quite large. So for example, if you have 10 materials in the image, you need the number of spectral signatures to be like 1,000, which is not reasonable either. So what we did is related to what is known for NMF, we use this separability assumption. So if we assume that for each material, it appears at least once purely in the data matrix. So for each material, for example, grass, there's at least one column of X that has the spectral signature purely. So this is related to the anchor word assumption. Here is for hyperspectral mixing. So this is this part of the matrix here. So we have 0. We don't have nonlinear effects. We only have the linear observation of pure materials at least once. Of course, it's a relatively strong assumption, but in practice, it's used and it works relatively well. So if the image is not, not too complicated. So under this assumption, we can design an efficient algorithm. And how did we do that? We just generalize an existing algorithm for separable NMF. So in separable NMF, it's the same assumption, except we don't have the nonlinear parts. So in NMF, this algorithm is called the successive non-negative projection algorithm. So how does it work? So you have your input data matrix X. So I just call R here, it will be a residual matrix. So at each step, you will extract the column of X with the largest L2 norm. And this essentially will be a vertex of the convection of the columns of X. This is by convex geometry. So if you have a set of points, if you take the points with the largest L2 norm, it will always be a vertex of the convection of the data points. And so you extract one vertex, then you project onto the set of vertices extracted. So you do a projection, and then you do this again R times, and you can prove that for NMF, this will recover the right W given that H is separable. I will go into the details, but please trust me if you want to know more. There is this paper about this, and so we are able to generalize this to this nonlinear model. So this is nice, although the model is more complicated than nonlinear. We were able to generalize these results, and the adaptation of the algorithm is relatively straightforward. Instead of doing the projection simply on the points extracted, you will do the projection onto this P2. So every component, every column of this thing, plus every componentized product of pairs of this matrix. So if you do this, you can prove that your algorithm will be robust to noise and probably correct under this assumption. So let me just show you a small numerical experiment. So here we generate synthetic data following this model, and we will have a nonlinear. So this is the separable parts, and the H prime will be the level of nonlinearity. So if mu is equal to 0, it means you only have linear parts, and if mu is equal to 1, this is only nonlinear. All the pixels come from nonlinear effects. So here are the results. So here, this is the original linear model for NMF, and this is the adaptation for the linear quadratic model. So yellow is good, such as yellow means good. Here you have the linearity effects, and here you have the signal to noise ratio. So given that the signal to noise ratio is large enough, so not too much noise, the linear quadratic successive projection algorithm works perfectly, which is not the case of the linear model. So it fails when there is too much nonlinearity, which was expected because it does not take into account this nonlinearity. This is what we observe here. So it's nice, it validates our theoretical results. What is also interesting is that if the nonlinearity is low, here, it's better to use a linear model, which makes sense because here, what we do in our model is we use this projection on more vectors, and so we lose information faster, let's say, intuitively. And so, so if the model is linear, it's better to use the linear model, which makes sense. And so now I will go quickly to the last part of this talk. It's very short, don't worry. So one drawback of linear models like NMF is that they cannot model nonlinear effects. I showed one example where we can counter that. And another thing that they cannot do is to learn a multilayer structure, which of course has been popularized by neural networks. And this makes sense in many applications. Many applications, you have layers of features. For example, in hyperspectral unmixing here, you have a first level with 8 materials. But then you can regroup materials. For example, you can regroup different types of trees into trees and different types of vegetation into vegetation. So it would be nice with a factorization to recover this multi-layer structure. And similarly, for this facial feature extraction application, you could have different layer of features, more localized features that combine into more global features like we see here. So this can be done with, so to extract one layer of features, you can use NMF. And then you can use deep NMF by adding layers, so essentially adding factors in the factorization. So it's a 2-layer NMF, and then you can do a 3-layer NMF, and so on. So of course, this is connected to neural networks. There was, in fact, a talk in this same series by Johannes Mali who discussed this. And here the difference is because typically in neural network, you don't have constraints on the factors, meaning on the weights between your layers. And so here, the main difference is that we don't have nonlinearity, but we have constraint on the factors. So it's closely related, but still quite different from an optimization and a theoretical point of view. And we have more interpretability here because we don't have these nonlinear functions in between. So in some application, it really makes sense to have this model. For example, in hyperspectral mixing, we can really extract layers of materials using this model. But this is quite recent. I mean, it has been introduced 4 or 5 years ago. And most people have used it in application, and there are not so much results regarding the identifiability, computations, applications. And so my goal is to go in this direction in the next few years. So voila, this concludes my talk. So I hope I convinced you NMF is a useful model. At least it has been widely used in quite a few applications, data analysis and machine learning, in signal processing. It's a hard problem to solve, so there are many challenges. And also there are challenges regarding the non-uniqueness. So even if you are able to design an algorithm that is globally optimal, you may end up with different solutions when you run it several times. And so this is also important to think about, especially in applications for uniqueness, where you really want to identify a ground truth that was generated, for example, from a physical model, like in hyperspectral mixing. So NMF has some limitations, and we can go beyond that. For example, extending to nonlinear models or deep models. So if you want to know more about NMF, I recently wrote a book on the topic, so you can check it out. And all the code from the book is available on GitLab, so you can run the examples presented in the book. The example I showed you was from the book. And thank you for your attention. So of course, if you have any questions, I'll be glad to answer them.
Thank you, Professor.
So thank you for the very, very, very nice talk. let me ask, are there any questions? From the audience? I maybe have one question to start. So here, when you go for your constraints for the non-negative matrix factorization, you usually assume that the factors have a certain rank.
Yes, we need to. I mean, most algorithms we need to input the factorization rank. Yeah.
Is there some stuff where instead of constraining the rank, you say, okay, I want both, or I just want, let's say, the weights sparse instead of having both things low rank?
So yeah, there are extensions for sparse non-negative matrix factorization where you want H to be sparse, and then you can also have approaches, which is also standard in matrix factorization, to try to, you can give a higher value of the rank. Let's say you have an upper bound on the rank, and then in the regularization, you will try to make, to remove factors that are useless. So for example, you can try to minimize the sum of the norm of the rows of H, it's the L12 norm, and so in that case, you may be able to set some rows of H to 0, which will reduce the rank automatically. So it's a kind of sparsity. So this has been used, in fact, in NMF, for example, but also for other matrix factorizations. This is quite standard. It's kind of a convex relaxation of the L0 norm of the norm of the rows of the H. So for each row, you look at the, for example, L2 norm, and you look how many are non-zeros, and you want to have as few as possible which are non-zeros, which will reduce the rank automatically. I don't know if this answers the question.
No, I was just wondering, I mean, either you constrain probably the rank, or you say, okay, I could actually have, I'm thinking about the nice example with the topics, where you could say, instead of having topics, you could have something, let's call it motifs, which are a bit smaller. And then a topic is made up of several motifs. So
it would be like an overcomplete dictionary kind of thing.
And then you could say, okay, maybe my my motif matrix is now overcomplete, but every sort of conversation contains these certain motifs, which then in some sense gives me the topic. And
yeah, that makes sense too.
Sort of a richer representation of what can happen.
In some sense, is what you also do in the deep NMF thing, where you would have very small things at the first layer that will combine into larger topics, let's say. So yeah, this is also related to this deep NMF thing, where you will extract at the first layer a very small topics, I mean, with very few words, and then at the next layer, you will combine them to make topics containing more words, let's say. So in fact, in this factorization, I did not go into much details, but the rank reduces at each level. So here, for example,
but then you would start, I mean, the largest rank, all the results there, how does the rank enter? Does it enter into does it enter at all into the result, or is it just?
Yeah, you need to choose. I mean, at least for this model, you need to choose the rank a priori, but in fact, this is a difficult question, especially for deep NMF. It's even worse because you have to choose a rank for each layer. So, for example, here I performed rank, I think it was 50, 25, and then 15, but it was quite arbitrary. So.
Yeah, of course, the official first, I mean, are you limited at first by the dimension of the problem, or, I mean, okay,
if you don't add any constraints, if you don't add sparsity constraint, then you are limited because, of course, you have always the trivial factorization x equal x times identity. So the rank has to be smaller than the dimensions. But if you add sparsity constraint, then you can go even, I mean, you could have the rank that is larger than the dimensions. That could make sense.
Yeah, no, I mean, in the classic case where you don't put sparsity constraints, in that case you're limited sort of by the dimension, right?
Yes.
Which,
exactly, yes.
Let's say, for the word count is not a hard limitation because the dictionaries are usually long books. But maybe
for example, in hyperspectral
chemical
mixing,
signatures.
you have also multispectral images. Sometimes you have only 10 spectral bands and you have more materials. Yeah. So in fact, we have a paper on that, and then we had to use regularization. So we had the factorization rank, which was larger than the number of rows of the matrix. And this makes sense
that would make sense to do in order to be bigger and then have more materials and then combine, like say glass plus concrete is a modern building, and if you have, I don't know, stone plus glass, it's an old building.
Yeah, exactly. So then you need either sparsity or some other regularization, like 2 sparse H, for example, like in your example.
So I've blocked you now. Are there more questions?
Yeah, Nicolas, can you say something? If I give you a matrix, let's assume the ideal case, it's positive and it has rank 7. Is there a way to know if it has a unique non-negative decomposition?
So first of all, what is interesting to know is that the rank of the matrix might not be equal to the non-negative rank. So for rank, there are, for example, rank 3 matrices that have non-negative rank higher than 3. So meaning that you need more than 3 non-negative factors to reconstruct it exactly. So this is a first important thing to mention. And in fact, in the book, in chapter 3, I discuss the non-negative rank notion. And so sorry, I lost the track of what I wanted to say. So if the rank is, I mean, in many applications, the non-negative rank will be equal to the rank because, for example, in hyperspectral mixing, you assume that the spectral signature are linearly independent if you have enough measurements. And so typically in let's say signal processing applications, you will have that the rank equals the non-negative rank. And in that case, you can estimate it using let's say classical rank estimation technique, like looking at the singular values, for example. But for more tricky problems, so there are some people working on that, more like linear algebra, more theoretical question about the non-negative rank, so which may be much larger than the rank. So there are some matrices where the rank is 3, for example, and the non-negative rank is not bounded by the, I mean, it's bounded, essentially it's proportional to the dimension of the matrix. I don't know if this was
And let me just continue there. So I assume that you have the rank and then you have a lot of noise, so that destroys the rank. But if I then magically give you the rank, does that help for the calculations also in the noisy case?
Yeah, of course. If you know the rank, so the true underlying number of components, then of course it helps because most algorithms they fix the rank as I mentioned, and they do some. For example, typically the most used approach is just a block coordinate descent method. You optimize alternatively over W and H, like in dictionary learning, because the subproblems are convex, and so it's relatively easy to solve, at least much easier.
And one other question. So if I just tell you, oh, this is the correct rank, but then the first time I was maybe overconfident and I gave you 7 instead of 8. And the other time I gave you 6 instead of 7. Do you have a feeling what happens if you go over or under? And assuming if I had given you 7, it would be unique. But now you overshoot or you undershoot. Do you still get, let's say, like most components and some get mashed up, or you get all components plus some nonsense, and then it's quite obvious what the nonsense would be in a generic sense? I mean, it doesn't have to be provable or anything, just a feeling.
So yeah, it's not so clear. For example, imagine your data points are kind of a square. And so if you do rank 3, you want to approximate it by a triangle. So it's just a visualization. And so it's not clear where the triangle will be compared to the square. So to the square. So it can get yeah, something quite messy if you don't have the right rank, let's say. So yeah, I mean, probably depends also on the structure of the data. If you can have additional assumptions. So if you, for example, you have separability and you shoot too low. So in this square example, I mean, yeah, you could have a triangle, but it could be any triangle that will fit the square, let's say. So it's a hard question, I guess. I don't have a good answer, but so yeah, it could mess things up a lot, I think. Yes, at least you could.
So undershooting is definitely bad. What about overshooting?
if you have overshooting and you don't impose regularization, then you have infinitely many solutions, of course, because you can imagine the problem is kind of the data points are make a cone that is close to the non-negative orthant. So if you have only 4 points and you don't have really a choice, you have this square you have to take. And then if you add 1 more point, then you can do many things. I mean, you can either not use this point or put it in between 2 points or put it a bit outside the cone and so on. So definitely it will also make the factorization not unique. And so that's why people use regularization in practice to avoid this type of things.
But yeah, okay, so it's not unique, but then is it sort of stable in the sense that if you use a stupid algorithm, like, I don't know, gradient descent, it will still go to the correct thing because...
I don't think so, no.
No, okay.
I think it will generate different solutions at each time. So if you don't regularize, no. It's not like in neural networks, I guess, where you have this kind of properties. Here, I don't think you would have that.
Oh, okay. Oh, thank you. So it's 11:07, but I think we have time for a couple more questions because there were the technical issues at the beginning. If we have one more question, I think that's fine. And if there's no more questions, because everybody noted down the book link, maybe we can show that again.
And also just for, so this is the link to my webpage for the book, but if instead of using NMF book, you use book NMF, then you get the PDF. So if you want.
Okay,
kind
so
of it's a hidden link. It's not public, but I mean, I can share it in theory, but so if you want to
everybody understood how to deprive Nicolas of all of his royalties of about 1 cent.
I prefer that more people read it than.
So if you promise to buy him a beer, because that will be much better than the 1 cent you get per sold book, I guess. You go for a book NMF. Yes. Okay. So Raphael said, thank you for the very interesting talk. Axel, if there's no more questions, I think we can close now.
Thank you.
Thank you very much for the